Our first speaker is Dr. Mona Javert, and she is a senior lecturer on the Internet of Things at Queen Mary University in London. She's a leading expert in mobile communication with a specialization in radio and backhaul design of cellular networks. Since joining QML in 2019, she started a new research group that examines the intersection between IoT and machine learning in the context of sustainable living. Three fast evolving research directions have emerged, where the first investigates multimodal data in the modeling of urban mobility. The second examines data preserving machine learning for smart energy and health. And the third elaborates the digital twin paradigm as a simulation platform for IoT-enabled sustainable living. In 2023, she launched a new multidisciplinary research lab entitled Digital Twins for Sustainable Development Goals, which features a multidisciplinary team for ushering in the SDG-related research through technical innovation related to IoT, AI, and digital twins. Mona, it's all yours.
So why don't you speak there?
Yeah, just speak.
No.
Sorry, just a second. I think somebody might trip over.
Yeah, just move it.
If you come this way,
Yeah.
I'll just.
Okay. Perfect. So thank you very much for the introductions, and thank you for having me here. Thanks for the organizers for inviting me. As it was said, my name is Mona Javert. I work on IoT and digital twins for sustainable development goals. And I'm delighted to be here today to talk to you about my research on how to use digital twins for sustainable transportation, and specifically looking at the safety of vulnerable road users and the sustainability of transport. So I'll walk you through some of the research that I've been working on. So why transportation? First of all, I'm sure you've heard a lot about the Sustainable Development Goals during these 2 days, SDGs. I'm focusing on the SDG 13, which is the climate change, and the SDG 11, which is the sustainable cities and communities. Last year was the midpoint between the time SDGs were conceived in 2015 and the time we're supposed to achieve those goals, which is 2030. And the committee met to assess how well or how bad we've done. And actually, we've done very, very badly. So we're all aware of the alarming rise in temperatures, global temperatures, that is causing extreme weather conditions. 99% of us people living in cities, we breathe polluted air. And it's more than that. This is now affecting even towns and smaller urban environments, not just the big cities. So this is quite alarming. And SDG is a serious problem that needs to be addressed. Perhaps technology can help us with that. Why transportation? Well, transportation is responsible for about 16% of the greenhouse gas emissions. And it is a good place to start. So this is where my research is centered. How can I make transportation more sustainable to address some of the SDG concerns? So what is intelligent transportation systems? It is using information and communication technology to inform and to advance existing transportation systems and to make them more safe, to make them more efficient, to make them more sustainable, to make them a better quality system. Some of the aspects of ITS that we focus on is the environment protection. How can we protect the environment while we still enable transportation of people? How can we look at the security? How can we look at the safety of vulnerable road users? How can we look at a good quality for a journey? When I came here today, I was really very glad to find that there's a bus that takes from where I live into just in front of this building. And that was really nice. This is a nice journey. The bus was on time. I have my GPS to know when the bus will be here, and everything was smooth. So this is enabled by ITS, by the location services, by the optimized journeys of these buses. This is what ITS wants to do. Now, the important part of ITS is information. Where do we get this information and how do we empower ITS? And again, ITS stands for Intelligent Transportation Systems. The Internet of Things is a good source of information, and I'll tell you more about it. And this is where my research starts, the IoT, the Internet of Things. The IoT generates massive amount of data. To interpret this data, we need some help, and this is where AI comes in to help us interpret the data and make sense out of it and create actionable insights that will be useful. Together, IoT and AI put together will help us create a virtual replica of the system that we're looking to optimize. And by having a virtual replica, which is the digital twin, it allows me to go and optimize that system in the virtual world. It's cost effective. It does not disrupt the happening in the city itself. And because it is a trustworthy replica of the system, I'm able to advance the research and find something that addresses the SDGs. So this is the story of today's talk. That's what it will be talking about. So why IoT? Well, IoT is very simply, it's a set of devices. We were just talking about it a minute ago. Now it's called IoT. It was called various other things in previous generations. It doesn't matter what we call it. What it really is a sensor. It's often a small sensor, as this one sits on the fingertip. It's a sensor which is equipped with some processing power, with some memory, and with the ability to connect to other devices or to the server. So this one, for example, measures the heart rate, and it communicates the data that it measures to the server or to other devices. Most of the IoT devices are often simple and low complexity devices. And that's what we call the IoT. All of those devices put together make the Internet of Things. So these are things that communicate together and that exchange data seamlessly without a human intervening to do this exchange of data. Why do I want to use IoT? Well, IoT gives me access to information anywhere on this globe at any time. Why does it do that? Because we have almost ubiquitous connectivity. Through our mobile phones, we're connected almost everywhere we go. With the satellites connectivity, we're connected really almost everywhere we are on this planet, even in the middle of the ocean. With that connectivity and with these devices, which are affordable, easy to deploy, it's just plug and play, I have information about what's happening anywhere on this earth at any time, in almost real time. So this is great. This is a good source of information for my ITS problem, Intelligent Transportation Systems. There are three categories of IoT devices that can be used for ITS. The first one is the road sensors. And these are sensors that make the infrastructure intelligent. So sensors that take information from the road itself. This is one category, and I'll talk more about it today. The second category is the vehicle-mounted sensors. So you've all seen, probably you drive some of those cars with all the fancy sensors, the radar, the lidar, the sonar, the cameras, and the ranging devices that give you all kind of information while you're driving. So these are sensors that are mounted on the vehicle itself. And there's a third type, which is the wearables. So these are sensors that we, as passengers or as drivers or as cyclists, we're wearing in order to get information and improve the ITS. So these are the three categories, and I'll talk about a project in each of these categories that is taking place in my lab. Starting with the road IoT sensors. So the first thing that I'd like you to see on this slide is there are two categories, what we call the disruptive sensors and the non-disruptive sensors. I think you can immediately see what that means. The disruptive sensors, I need to stop the traffic on the road in order to deploy that sensor. The most simple one is the pneumatic sensor that you see up there. So the pneumatic sensor is really the most simple one. I've seen it for the last at least 40 years. And it is used to count the number of cars passing, to get the speed of the cars and the direction of movement. A very simple sensor, but simple information as well. The most complex one, and the one that gives me the most information, is the camera-based sensor. Camera-based sensors can tell me what's the color of the car, how many people are in the car, what are they wearing, what's the color of their faces, what's the number of this car. All the information is captured with the camera, which is very good. Some of it is not needed for ITS. And it comes with also challenges. So the first project that I'd like to talk to you about today is an alternative road IoT sensor, which is based on fiber optics. So this is the fiber optic, which is usually an infrastructure for communication, but we're going to use it for sensing, and I'll tell you how that works. So this project was championed by Cheyenne, who's about to complete her PhD, and it got the first prize award in a student competition of IEEE ComSoc last year. How does it work? The fiber optic is the blue line that you see there. That blue line is underground. So it is underground, it's covered, you don't see it. And it's attached to a DAS interrogator, which is this blue box over there. What the DAS interrogator does is it sends a light signal from that point over there. That light signal propagates all over the fiber. When it reaches the end of the fiber, it gets reflected. That's the normal operation. But while this is happening, there's also a backscattered signal which reflects back. This backscattered signal carries a lot of information, and it is affected by any change along this fiber. It is specifically affected by acoustic signals. Acoustic signals, such as a car driving on that road, causes vibration. This vibration changes that backscattered signal in a unique way. This backscattered signal goes back to the DAS interrogator and it gets captured, gets analyzed. This technology has been commercialized for a long time, and it's used to detect the location of acoustic events. It's used for monitoring the security of peripheries in remote areas, for example. It works very much like the radar. Yeah? With the radar, you send the signal. When it reflects, you measure how long it took from the time you sent it to the time it was received, and then you know that there's an object at this location at this time. This is the same principle, but it's along the glass in the fiber optic. So that technology existed. What we did with that is to try to get information from this technology to answer ITS questions. Before I tell you exactly what we did, let me just walk you a little bit through how this works. So the technology is OTDR, which is optical time domain reflectometer. And it's really about measuring any change along the fiber. And this change could be change in temperature, could be strain, could be physical disturbance. It could be a rat biting into the fiber. They like to do that. And it could be the acoustic disturbance. We're interested in capturing the acoustic disturbance, such as the vibrations caused by cars when they drive along the car, or when they drive along the road. Just a bit of perhaps a reminder of how light propagates. Light propagates because of the reflective index. We all remember from our school days how when you have a straw in a glass of water, it looks like it's broken or it's angled. So this is kind of visual illusion because of the reflective index. But that reflective index is what causes the light to go from the source to the end. It keeps on reflecting back and forth in this glass until it reaches the end. As I said, when it reaches the end, we have a main reflected signal, which is called the Fresnel reflection. This is a very strong signal. We're not interested in either the signal that is transmitted nor the main one that is reflected. We're interested in the Rayleigh backscattering. The Rayleigh backscattering occurs when that light is incident with a particle of the size which is smaller than the wavelength of the light. It could be an impurity, it could be a particle in the glass. And when this happens, some of the light signal will reflect back. And this is what we call the Rayleigh scattering or the Rayleigh backscattering signal. Very much to wireless communication, if anyone is a wireless communication background. When that signal goes back, what we do in our DAS system, in our OTDR, is we filter out all of those signals, which are 20,000 times stronger than the Rayleigh signal, and we only focus on the Rayleigh backscattered. And this is what the signal looks like. This is the location along the fiber, and this is the component of time, and this is how that signal changes over time. That's the intensity of the signal. By analyzing this signal, we can tell a lot. And I'll prove to you that you can tell a lot in a second. But perhaps you'll say, well, this is very complicated. I've got cameras. Cameras are cheap to deploy. Why do I want to go and bother and put the fiber underground and attach this DAS and then filter this signal? And why do I want to do that? Well, for a few good reasons. I hope that you also think there are good reasons. First of all, I don't have to lay fiber every time I want to use a DAS system, because we often have dark fiber. So this is fiber that was laid and is not used. So we can reuse this dark fiber for this system, and it's almost everywhere. I could, for example, cover the road between London and Oxford by only attaching 2 DAS interrogators to the existing fiber. And that would give me continuous information about everything that is happening along that road, only with 2 DAS interrogators. If I was to cover this with cameras, I would need 1,000 cameras. And it would still be interrupted, and I would still need to re-identify every vehicle and every visibility of camera. That's number one. Number two is cameras work less well when it's foggy, when it's rainy, when it's dark. DAS couldn't care less about what's happening because it's underground, right? So it will give you the same information no matter what's happening in the weather. DAS doesn't capture personal information. So cameras will give me a lot of information. A lot of it is not useful. I don't think ITS needs to know what's my gender, what's my age, what's the color of my hair. DAS doesn't capture this information. And perhaps one of the most strong points of DAS is that it cannot be fake. So this is not Morgan Freeman. This is a fake video of Morgan Freeman. There's no way on earth anyone can generate a fake DAS signal of me walking along the road. Nobody knows how to do that. But fake videos are, anybody of us can do that. So all of these are reasons why I think DAS is important. Great, but can it still tell me information that is important for DAS? I haven't answered this question yet, and I'll answer it now. So in order to answer these questions, we worked with our industry partners, and we went to Spain, south of Spain, and we laid our own fiber. We didn't use an existing one. So this green line there is our own fiber. The DAS interrogator was located here. The purpose of this experiment was to understand how traffic changes when moving from outside the town into a town and vice versa. But we took that opportunity to collect data for ourselves, for our research, which is to identify which car is moving at any point and how many people are sitting in this car. So we used these 5 different cars, and we collected DAS signals. So what I'm showing here is the DAS signal, which is produced by each one of these vehicles. If you just look at them, they do look different, right? You can see that there's a special signature for each one of these cars. And indeed, it is. We also did an experiment with the Renault Clio. And what we did is we drove that Renault Clio up and down with different number of passengers. And the first thing to see is you see the same trend, exactly the same one, but the peaks and the troughs have different values. And this has to do with the number of passengers that are sitting in the car, but not just the number of, not the total weight, it's also the distribution of the weight in the vehicle itself. So by just looking at these, we can see that there are some characteristics in the DAS signal that tell us which car is driving. And if I know which car, it'll tell me how many people are in this car. And then the question, could I train an AI model to do that for me? Because the DAS data is massive. And for me to go and look at each one of them will take forever. So can I tell which car is driving? And the answer is yes. We tried 2 different approaches. The first one takes 1 point along the fiber, and it takes the variation of the DAS signal over time. So the x-axis is the time, and that is the intensity. And we fed this into a deep neural network, and we were able to answer the question with 94%. And then we said, let's try to do it better. And we were able to do that by taking 6 points along that fiber. And the 6 points is not a random number, it's because that covers 4 meters, which is on average the length of a car. And when we take all of that information and feed it into a neural network, then we can answer this question with much better accuracy, 99%. And then moving on to the other question, can I tell how many people are in the car? I can, but on condition that I know which car it is. So I have to know which car is driving. And if I do know the car, then I can tell the number of passengers in this car. Again, we tried both methods. The first one would give us 91%, the second one would give us 94% accuracy. So this is telling exactly how many people are in the car. Why is this information important? Why do I want to know which car is driving? Why do I want to know how many people are in the car? Why are these important for ITS? Well, they are for various applications. We've all seen ULEZ. ULEZ is a method to control the emissions by controlling the type of vehicles that is driving in certain areas. So if I can tell which car is driving where, then I can enforce ULEZ. Knowing the number of vehicles, knowing the number of passengers in a vehicle will help me to regulate and control the high occupancy vehicle lanes, such as these ones. Knowing which car is driving will allow me to prioritize emergency vehicles, and so on and so forth. So I hope that I've convinced you that DAS is an alternative road IoT sensor that carries a lot of information, which is very useful for ITS. And then we wanted to know, we've done all of this work with cars. Cars are massive vehicles, and the signal is strong enough. Can we do the same for active travel? And we were awarded £500,000 to go and investigate this question. And we went there, so myself and Cheyenne, we went and we collected data with a skateboard, with a scooter, with an e-scooter, jogging, running, with a bicycle, and all so on and so forth. And Uri Kang is the person who's running this project at the moment. And we have some early results, which haven't been published yet, but I'm happy to share some of those with you because I find them very beautiful. And I hope that you find the beauty in that as well. So these are 6 different signals, DAS signals, that were collected while Xiayan, my student, was doing an activity, either walking, jogging, cycling, skateboarding, or e-scooting. And if you look at them, again, they all have very distinct features, right? They look different. And so this is the game that I like to play. So this is Cheyenne either riding an e-scooter or a bicycle. And first thing to see is that both of these activities is about rolling with 2 wheels. And both signals have similar features, except one has higher frequency than the other one. One has higher intensity than the other one. So do you think A is cycling or e-scooter? If you think it's cycling, raise your hand. Yeah, all right. So it's the other way around, actually. And I'm doing this on purpose. And the reason is, first of all, cycles have larger wheels. They go faster. And the intensity of this signal is higher. And the reason it's higher is because e-scooters are very heavy. And I know that because I had to carry this from Waterloo down to Fleet, where we collected this data. And it's heavy because of the battery. So the e-scooter is much, much heavier than the bicycle. And you can see that the weight of it creates a higher intensity, but a lower frequency. This is a higher frequency. So thinking about that, which one do you think is jogging and which one is walking? So B has higher intensity. Is B walking or jogging? Okay. Yeah, exactly. So just because of the impact, that you make while you're driving. And this is the funny one. Oh, it's funny and interesting. So this is riding a skateboard. I can't skateboard. Cheyenne can. I was lucky that she can. And if you do, I don't know if any of you do that. So part of skateboarding is, again, standing on the skateboard and rolling. And that pattern here, which is similar to the bicycle or similar to the e-scooter, shows that part of the skateboarding. It's much more noisy because the wheels of the skateboard are smaller and there isn't suspension. So the vibrations are really felt throughout. And then another part of skateboarding is really kicking the ground to give yourself a push. And that's what you see there. So both of these signals are skateboarding. So I think it's beautiful. And at the moment, Rikang is looking at training an AI model to detect these activities. And that's the end of that talk. I talked about IoT sensors for the road to make smart infrastructure. I talked about existing sensors, and I talked about a new sensor, which is based on DAS. The second topic is looking at IoT sensors that are mounted on vehicles. And as I said, there's a plethora of different types of sensors that we have in our cars these days. The project that I'm working on looks at the front cameras of the car. And specifically, the ITS problem that I'm looking at is making vulnerable road users feel safe. And these vulnerable road users probably feel less safe with autonomous vehicles and driver-assisted vehicles on the roads. For a simple reason. Those of you who drive, and I'm sure that you're all good drivers, you're driving down the road and you see kids playing with the football on the side. You immediately start being more careful because you know that they're going to jump in front of the car at any time, right? Computer vision, which is used by autonomous vehicles to understand the scene, to interpret the scene. Computer vision is very good at classifying objects, detecting and classifying objects, to know what is around, but it's less good at predicting the intent of people, which is our common sense. We can predict that the kid playing with a football is likely to jump in front of the street. Autonomous vehicles are not designed to do that, not just yet. And one of the challenges is, can we train these autonomous algorithms to predict what a vulnerable road user is likely to do in the next sub-second? So this is another project which was championed by Cheyenne, and she looked at video footage taken from cameras and positioned at the front of the vehicle. And from these video clips, she processed it in 3 different pipelines. The first one is taking the skeleton of the person. So the skeleton is just the key points of the person. The second one looks at the surrounding image as a context, what's happening around this person and how is this scenery changing over time. The last one is looking at the trajectory. So how is this bounding box, which is the red frame around the pedestrian, how is the position of that changing from one frame to another? And that will indicate how this person is moving. So she's trained a model for each one of these data streams, and then she's used a contextual ensemble learning approach to fuse the knowledge from these models and to answer the question, is she crossing or not? And she got the first prize of the IEEE Intelligent Transportation Systems Society Student Challenge last year to predict the behavior, and her results were 13.6% better than the state of the art, 20% less complex method, and she was able to compress the data with more than 4,000 times, which is very important when we know that this data is being transmitted over the internet. So we want to compress it and we want to just extract the useful information. And this is the third project that I'll talk about and the last project that I'll talk about, and it's about wearables. And the wearable is this GoPro device that you see at the helmet of the cyclist. And wearables are devices, IoT sensors that we have on our body or on our equipment that can also inform ITS. So in this context, we were looking at the cyclist road safety. And what we did last July, not 2024, 2023, we worked with a group of cyclists who have a challenge every year called All the Dogs. And what they do is they form 5 different groups of cyclists. And the challenge is to go to all the docks of the Santander bicycles in one area. So the blue area, the orange, and so on and so forth. And what we did last year is we said, can you please have a GoPro on your helmet that takes information while you're cycling? And the information that we wanted to collect is the video footage or the still images. You want to collect the GPS information. You wanted to collect accelerometer and gyroscope data. And with that, we wanted to answer 2 questions. The first one, can I calculate the roughness of the surface? So I don't know if any of you cycle, I do, and I hate it when the road is really very bumpy. It's just not comfortable, and I don't think it's safe as well, because I'm always trying to move away from the pothole or from the kind of rough area, and that puts me at risk when there's a bus on my right. So the first one is we wanted to calculate the roughness of the surface. The second one is we wanted to predict the perception of safety. So if I ask you which image looks more safe for you, for me, I feel very safe here because I have a dedicated cycling lane. There's a separation between me and the cars present, whereas in this area, I'm completely exposed and I wouldn't feel safe here. If I ask my son, he'll tell me, they're both very safe. You're just being a chick. So that's, but the difficulty in that is how can I go and train an AI algorithm to understand the perception of safety, because it's a very personal thing. And we've been trying to do that and we haven't been very successful yet. And the reason is we asked 3 different people to label each one of these photos and they completely diverged. So what we're doing now, we're still in the process of doing that. And we're focusing on data in my end. This is where our university is. Let me see. So our campus is here. This is where we live. And we're collecting data along that triangle. So at the moment you can see some of those. I'm gonna see if that works. No. I wanted to show you the website. That
Left.
oh, that one.
Yeah.
I probably will not remember the password actually. No, I'm going to move away from that and continue. I'll just tell you what it does. Right. So we're building this website, and each of these points, you can see some yellow points there and some gray points. When I click on those points, it will open an image. And this is an image that was taken from this point. It will show you the roughness index, and it will show you. I'm not sharing. And it will allow participants to go in them are secure, some of them are less secure, some of them give you long range, others give you short range. Some of them are licensed, others are not licensed. Some of them have quality of service guarantees, others don't. Which one do you choose? And we usually go by selecting this based on the costs and based on the performance. And what needs to be brought into the picture is to make this choice based on the energy efficiency. Which one gives me the most energy efficient solution to connect these IoT devices? So this is still an open question. And that's it. Another thing, I talked about it a little bit earlier, is that these devices are usually very small devices, very simple, lightweight, meaning that they have little processing power, they have little memory, they operate on battery with limited battery, and still they carry a vital role, like a pacemaker, or they control the autonomous vehicle. But because they have such limited processing power and memory power, it's very easy. They are vulnerable for a malware attack. But they cannot host a sophisticated algorithm for malware detection. And this is one of the challenges. How do you secure the IoT devices themselves? How do you come up with an algorithm that is very strong, but that at the same time is simple and can be hosted in these simple devices? The third challenge is the data torrent. So I said earlier, 15 billion IoT devices are connected today. Now these 15 billion devices, they generate almost 70 zettabytes of data. That's more zeros than I care to count. The thing is that most of this data is garbage. We don't need all of this data. I showed you earlier that if I take all of that image, the only points that are important to predict the pedestrian intent are these red dots out of all of that image. So this is high compression already of the information. And if I can do this at the edge where this data is generated, then I save bandwidth on my wireless communication. I save storage space in my cloud. And it's good because I'm getting rid of the garbage. So this is a big challenge of how do we go and do that? And another technical challenge is the carbon footprint. So I'm sure you've all heard of the large language models. To train a large language model produces more CO2 than 5 cars during their lifetime, right? So if I was gonna throw LLM at the ITS problem to reduce the CO2 of vehicles, while I produce more CO2 than these vehicles, what's the point? And it is important to be aware of the carbon footprints of the devices themselves that consume energy, the network that consumes energy, the storage of the data that consumes energy, and the AI that we use that also consumes energy. So these are the technical challenges which are still there, still out there. And the last bit is the non-technical challenges, which I'd like to talk about. I find this one the most difficult one, and perhaps multidisciplinary is the approach to solve these kinds of problems. So a brilliant technical solution, and we engineers, I think most of us are engineers and data scientists in this room, we tend to throw technology at a problem, and we think that it's going to solve it. It does in our mind, it does on our screen, it does in the paper that we published, but in real life, sometimes it doesn't. Because if that solution is not accepted by the public, then it's useless, right? I mean, ULEZ, in my opinion, is a brilliant solution. Last week, I was reading in The Guardian that because of ULEZ, children who live in this area started using active travel more. So 3 in 10 students started using active travel to go to school, in addition to what it was before. The performance of these students improved because of ULEZ. So there are facts that says that the ULEZ is better. Still, there's lots of resistance against it. And it doesn't mean that these people don't have a point, those who resist ULEZ, they do have a point, but we need to understand it, we need to capture it in our solution. Other examples, during COVID, there was a conspiracy theory that 5G caused COVID. And people started attacking antennas and burning antennas and so on and so forth. Again, 5G is important. If it wasn't for 5G, for wireless communication, we just can't talk to each other. I can't exist without it anymore. various other things, vaccines. Some people think that climate change is just fake news and it's not there. And I think a lot of what we see there is because that we kind of throw technology at a problem without having the engagement of the public from the onset of the project. And this is something that we're looking to change, where every problem is formulated with the public and every solution is designed with the public as taking part in that as a stakeholder, really. And this is the what we proposed at Queen Mary. So this is a new research lab that we started last year. We call it Digital Twins for Sustainable Development Goals. And it is led by social science. And it's the social science that makes that bridge with the public engagement. It is shaped by domain experts. So the moment we're looking at transportation, we're looking at public health, and we're looking at air quality and climate change. And then we throw our nice technology at the problem once it is well defined and understood and comprehended. So it's very much a multidisciplinary research lab. The other thing that we're doing, the reason we have digital twins is for twofold. The first one is a digital twin allows me to test and validate scenarios in the virtual world. And it also allows me to avoid these extreme cases where, yes, in order to reduce the CO2 of cars, I use an LLM, which produces more CO2 than the cars themselves. So these kinds of circular, if you wish, vicious circles of solving a problem from one end and creating a larger problem are solved with that. And this is the last slide, just to give you an idea of how we do our digital twin. So we're looking at the digital twin of digital twins. And this is where we avoid this kind of problem. We look at the holistic solution. And that's the last slide. Thank you very much. And if you have any questions.